The sum principle says if A and B are disjoint finite sets, disjoint means they have no element in common. You can get the cardinality of the union of these sets by just adding the cardinality. So we can apply this principle when we have a way of breaking up the set that is completely exhaustive, so it covers everything, and mutually exclusive. So there's nothing in common between the way we've broken it up. So we're going to come back to our friend Bob here. Bob only has red socks and blue socks. And I wanted to turn this into a practice question, but then my mind wandered. So I'm going to need your help to finish this. We turn this into a question that involves the sum principle. How many socks does he have in total? We use the sum principle when we have something that's completely covered by two cases. Is this enough information to finish? You know the number of each color sock. So will you give me a number for each color sock? Okay, so he has 12 red socks and 8 blue socks. How many socks does he have in total? 20. Now people think this is too easy. People think, what if there's a sock that's both red and blue polka dot? What if there's a sock that's red and blue stripe? And that's kind of a situation where if you were doing this problem in the quote unquote real world, you'd probably be doing it for a client. Bob has a lot of money if he's going to ask some questions like this, but you'd be able to talk to the client and you'd be able to get kind of engage in a conversation. If you see something like this and it seems like the problem is simple, I'm not going to intentionally try to trap you by withholding any information. Now, it may be that there's information that you need to know that isn't in the question, but I'm not going to have like secret red and blue socks that are striped to mess you up. So that's the sum principle, and it's relatively straightforward. Does that seem clear to you? Now the thing is, once you have done this, and once you have the basic idea, now you want to look at it and say, how could this be more general or more complex? And think about this. This sum principle depended on having two disjoint finite sets. So they're kind of three conditions. Two sets, they're disjoint, and they're finite. What we can do to start exploring this is we can start bumping it just a little. We can ask if something doesn't go our way here to make it a simple, straightforward thing to apply. So what are the situations that could occur that aren't as simple? We have two disjoint finite sets as our starting point, and could look at generalizing that to more than two disjoint finite sets. Good. What's another way we could look at generalizing? That only changes one thing. Okay, so we have two finite sets, but they're not disjoint. And what's the other way we could look at generalizing? We could have two disjoint sets, at least one of which is not finite. We could have two disjoint sets, at least one of them is infinite. About each of these situations, we want to think about finite sets mostly. And so for now, we'll leave that alone. Although y'all said that if at least one of the sets is infinite, the union has to be infinite, then it's really like, how comfortable do you feel writing this? How comfortable do you feel saying something is equal to infinity and something more squirrely about it? And we'll just forget that ever happened for now. So y'all were looking at more than two disjoint finite sets. What did you joint finite sets? And you're saying the cardinality of x1 union with x2 union, all of them together is equal to what? All this is saying is that as long as everything is disjoint, the same pattern applies that you just add up. And then what about two finite sets that are not disjoint? So there's also a joke. A bunch of finite sets that all don't have anything in common, and you want the size of all of them put together, you just add up all the sizes. Notation. Two finite sets that are not disjoint. So I have A and B, but maybe there's some overlap and they're not mutually exclusive. So here are three different rules to deal with three different situations. And what I like about it, but I like it because they're in these different representations. We'll come back to these rules later. This is the one that we really want to make sure we have our head wrapped around right now. But if you know this one also, it won't hurt you, because I think that's the really cool thing about discrete structures is you start with these things that look really simple and obvious. Sometimes you have to think carefully about, but then once you understand the simple and obvious, you can build on and end up with something that's still valid because you understood the principle of the structure.